Chapter 5, Module 3. In this module, we shall introduce two very important terms. One is contractible space and the other one is homotopy equivalence. Now, what is contractibility? Intuitively, a space is said to be contractible if we can squeeze or shrink the space to get a point space. So, that is what our intuition suggests, that given a space, shrink it and get a point. If it can be done, then it is contractible. Now, in this module, we are going to formalize this intuitive idea in mathematical terms. On the other hand, homotopy equivalence is a generalization of homeomorphism. We know that two topological spaces are called same if they are homeomorphic. Now we want to relax this homeomorphism, idea of homeomorphism, and generalize it to get the definition of homotopy equivalence. We show in this module that these two terms are actually interrelated. The idea of squeezing a space to a point can be restated in terms of continuous deformation. Consider the identity function I from x to x and the constant function c from x to x0. Squeezing a space x to a point x0 is as good as asking for capital I to get continuously deformed to the function capital C. So, we define it formally that a topological space capital X is said to be contractible if the identity map Ix from x to x is homotopic to a constant map Cx0 from x to x, where x0 is a particular point chosen from capital X. It is not hard to see that Rn is contractible, the n ball in Rn is contractible, which is definitely a convex subset of Rn. In fact, any convex subset of Rn is also contractible. So we generalize it a bit more in the next example. If we take any star-shaped subspace of Rn, then it is contractible. Now, what do we mean by star-shaped subspace? A subspace of Rn is said to be star-shaped if there exists some point x0 belonging to capital X such that Tx plus 1 minus T of x0 belongs to capital X for each x belonging to capital X and for every t varying over the closed interval 0, 1. So, obviously, any convex subset of Rn is star-shaped, and therefore, all these examples that Rn, Dn or any convex subset of Rn are contractible follows as a special case to this example. Define H from x cross I to x by Hxt is equal to Tx plus 1 minus T of x0. Then this capital H is a continuous function. Hx0 is small x0. That means it is equal to Cx0 evaluated at any point x. Hx1 is small x, that is identity function evaluated at the point small x. Therefore, Cx0 and Ix, these two are homotopic via the homotopy capital H. Now, we show a very important theorem and we feel that it should be that a contractible space is path connected. Now, if I start with a contractible space capital X, then by the definition of contractibility, we must have a point P in capital X such that the identity function on the space capital X, that is Ix, should be homotopic to the constant function Cp, and we denote that homotopy by capital H. For capital X to be path connected, it is enough to join any arbitrary point A of capital X with the given point P by a path, because we know that if we have any two points A and B in the space capital X and we want to join them by a path, it is enough to join A with P and P with B and take the product of paths. So for each A belonging to capital X, we define a function WA from I to x cross I by WAT is equal to AT, the pair AT. Now this is of course a continuous function for each A belonging to capital X. Now we have this diagram that WA is a continuous function from I to x cross I, capital H is a continuous function from x cross I to y. So the composition of two continuous functions is a continuous function, therefore H composed WA is a continuous function from I to y. So we have a path, H composed WA is a path in y such that H composed WA evaluated at the point 0 is A and H composed WA evaluated at the point 1 is P. So H composed WA gives us a path joining the points A and P. So the question is path connectedness a sufficient condition for a space to be contractible? We have a feeling that the answer should be in negative. To support our guess, we may consider the example of the unit circle, that is S1. We can easily visualize that S1 is path connected. Given 2 points on S1, we can always join them by a continuous function, by a path. Is S1 contractible? Our intuition suggests that answer is no. We eventually establish mathematically that S1 is indeed non-contractible. In the definition of contractible spaces, we demanded a distinguished point x0 such that the identity function on the space will be homotopic to the constant function at the point x0. So that means, if we state it intuitively, that we want to squeeze the space to the point x0. Now of course, we feel that if a space can be squeezed to a single point x0, then it can be shrunk to any point of the space. We want to formalize this idea of squeezing to any point of the space mathematically. For that, we prove this theorem. It is more general theorem that any two continuous functions from a topological space to a contractible space are homotopic. Suppose f and g are two continuous functions from a space x to a contractible space y. Then there exists some point y0 belonging to capital Y such that identity function on y is homotopic to the constant function cy0. Now it is known that being homotopic to is an an equivalence relation. So F is homotopic to F, and we have already proved earlier that composition of two homotopic maps are homotopic. So identity composed F is homotopic to Cy0 composed F. Now, if we look at the function Cy0 composed F, then we see that it is actually the constant function which maps every point of x to y0. Let us denote that constant function by Cy0 cap. Similarly, doing the same thing with the given function g, we get that identity composed g is homotopic to constant function Cy0 composed g, and this Cy0 composed g is once again the same function Cy0 cap. Hence, F, which is equal to identity composed F, is homotopic to Cy0 cap, and this Cy0 cap is homotopic to identity composed G, which is G. So applying the transitivity of the relation being homotopic to, we get that F is homotopic to G. Now, as a corollary to the theorem, we get the desired result, that a space X is contractible if and only if the identity map Ix is homotopic to a constant map Cx for any x belonging to capital X. This is what we were looking for. Now, how do I prove it? Using the previous theorem, as X is contractible, the codomain is contractible, and therefore identity and the constant function Cx for any x belonging to capital X will be homotopic. And the converse is obvious from the definition of contractibility. Now, we introduce the other important concept of homotopy equivalence. The idea of homotopy equivalence evolved from generalizing homeomorphism by replacing the equality by the relation that two functions are homotopic. So the definition is a continuous function f from x to y is said to be a homotopy equivalence if there exists a continuous function g from y to x such that the composition g composed f is homotopic to identity and f composed g is homotopic to the identity on y. Now we see that in case of homeomorphism, we were looking for g composed f is equal to identity and f composed g is equal to identity such function g. Now in such case, f and g are called homotopy inverse of each other, and x and y are said to be of the same homotopy type. It is easy to deduce that two homeomorphic spaces are of the same homotopy type. Now the next example shows that homotopy equivalence is a proper generalization of a homeomorphism. Consider a unit disk D2 and take any point x from D2. Let us take the point space capital P consisting of the single point x and consider the inclusion map I from P to D2. Now, if we take the constant function Cx, then Cx composed I is exactly equal to the identity function on P. There exists a homotopy capital H from D2 cross I to D2 defined by hzt is equal to 1 minus t times z plus t of x. That is the convex combination of x and z. Now this capital H is certainly continuous. If t equal to 0, then hz0 is z, that is the identity function evaluated at z, and if t equal to 1, then hz1 equal to x, which is identity composed, rather inclusion composed Cx evaluated at the point z. Hence, inclusion composed Cx is homotopic to the identity function on D2. We now show how contractible spaces can be characterized through homotopy equivalence. A space is contractible if and only if it is the same homotopy type with a point space. Now, what do we mean by same homotopy type? If given a topological space X and given another topological space Y, then we are looking for a homotopy equivalence between them. If there exists a homotopy equivalence between them, then X and Y are called the same homotopy type. Now, in this case, we are to show that if the space is contractible, then we can find a point, rather a point space such that capital X is of the same homotopy type with the point space. So, capital X is a contractible space. By definition of contractibility, we are going to get a point x0 from capital X such that the identity function is homotopic to the constant function at x0. If we take capital P as a point space and define a map capital C from x to P by the constant function which takes all the points of capital X to the point P, define a function small f from capital P to x by Fp is equal to x0. There is no other point in capital P. So, the only point P belonging to capital P will be mapped to the point x0 which we have already got from the definition of contractibility of capital X. Then C composed F is identity on P and F composed C is homotopic to the identity function Ix by the homotopy capital H. Hence, this contractible space capital X and the point space capital P are of the same homotopy type. Conversely, suppose there are continuous functions g from capital X to capital P and h from capital P to capital X such that g and h are homotopy equivalence. That means G composed H is homotopic to identity on P and H composed G is homotopic to identity on X. Then we have to show that capital X is contractible. Now, let us suppose that the function H takes the point P to some point Q in X. And there is no other choice for G because G must take all the points of capital X to the only member small p of capital P. So, it is a constant function and therefore, the composition H composed G will take all the points of capital X to the point Q of X. Now, H composed G is mapped which takes all the points of capital X to the point Q. It's a constant function CQ, and by the given condition H compose G is homotopic to the identity, CQ becomes homotopic to the identity. So by the definition of contractibility, X is contractible. So from this theorem, we get a corollary that any two contractible spaces are of the same homotopy type. There are several examples of non-contractible spaces which are of the same homotopy type. One such is given here. We take the annulus A, that is all the points Z belonging to the complex number C, such that modulus of the complex number Z lying between 1 and 2. We take the circle, the unit circle S1, and define a function f from A to S1 by fz equal to z by mod z. Then of course f is a continuous function, and if I take the inclusion map I from S1 to A by z sending it to the same z, then f composed I is identity on S1, and I composed f is homotopic to identity on A. Hence, capital A and S1 are of the same homotopy type. Now, if we take a connected space capital X and we take a disconnected space capital Y, then capital X and capital Y are not of the same homotopy type. If possible, let X and Y are two spaces which are of the same homotopy type. Then there are continuous maps F from X to Y and G from Y to X, such that G composed F is homotopic to identity on X and F composed G is homotopic to identity on Y. So, if we take that homotopy F composed G to identity on Y as capital F, then Fy0 is F composed G of Y and Fy1 will be Y for all Y belonging to capital Y. Since Y is disconnected, there are open sets U and V which are non-empty, such that capital Y is disjoint union of U and V. So there exists a continuous function P from capital Y to AB such that P of Y is A whenever Y is taken from U, and P of Y is B whenever Y is taken from V. Since X is connected, f of X will be contained totally within U or totally within V. Without loss of generality, we assume that fx is contained within U. Choose a point V from capital V. Such a choice of V is possible because V is non-empty. Define a function h from I to AB by ht is equal to P of capital F Vt. Then h0 is A and h1 is B. That is, H is a continuous surjection from a connected set I to point space AB, which contradicts the connectedness of capital I. So this proves that whenever we are taking capital X a connected space and capital Y a disconnected space, they can never be of the same homotopy type. In the last theorem, we have seen that connectedness can be used to distinguish between spaces which are not of the same homotopy type. We conclude this module with a note that another topological property, very well-known topological property, that is compactness, cannot be used for a similar purpose. Because if you take an open disk, then an open disk is a non-compact space, and if we take a point, then a point is a compact space. But we have already seen that an open disk can be squeezed to a point, so they are of the same homotopy type.